Feynman, Chapter 2, Section 1, Basic Physics. Feynman begins this chapter by describing how the science that we're concerned with surrounds us in myriad forms. It's everywhere if we look. He uses the example of the seaside as a place where we can see physics in all of its forms. We see with the water itself and the motion of the water sloshing about and the waves. More than that, above it we see the blueness of the sky and the sun. We also see rocks and pebbles of various different permanences and hardnesses and textures. He says that we see the seaweed and the animal life, but importantly, we are there, the observer, and that makes a difference too. But then Feynman points out that it is always as complicated as this. Whenever we see nature, we see all of the competing influences and pressures. But what he asks is whether or not there is anything elemental that is underneath all of these things that we see. That is the laws of physics. So I'm going to have a look through this microscope at some sand. Just a few little grains. On they go. We're going to have a little look, see how they appear. Let's have a look. Come and have a look. And here we have it. Sand through a microscope. And as you can see, it's just lots of little rocks. What's really interesting here is that the grains of sand are exactly the same as this massive lump of quartz. So this giant rock is basically exactly the same, just on a different scale as the grains of sand. Now that means by understanding this rock, we can understand the grains of sand. And actually, we can go the other way as well. Understanding the grains of sand enable us to understand a little bit more about the rock. Now I'm going to put that to the side, because I want to show you this. This is 4 billion year old anorthosite. It's a mineral. It's one of the oldest rocks that you can find anywhere on Earth. This sample has come from the Outer Hebrides. And scientists have found that this mineral is the same as what has been recovered from the Apollo moon landings. That the moon is made out of this mineral, 4 billion year old anorthosite. Now, what we can do, and I'm going to place the gloves on for this, is if we consider that this one stone here is to a larger body what a grain of sand might be to this giant quartz crystal, then we can use our understanding of the small parts to get an understanding of the whole. And I'm being very careful how I handle this, because this is 140 years old. These in our collection are some of the original first drawings of the surface of the moon, drawn with a telescope. And so our understanding of the anorthosite mineral as a grain of sand on the celestial body of the moon enables us to understand a little bit more about the moon. Understanding that there's no obvious difference between a stone and a grain of sand, or even the moon, enables us to simplify on the number of things in this picture. There are not as many different things if we consider certain things to be similar to each other. But there are red herrings in this approach. I've got some water here, and I'm going to add a dye to it known as fluorescein, just so that you can see it a little bit better. I only need a tiny amount of this, just a drop, and in it goes. Now fluorescein makes water a wonderful luminous colour like this, as you can see. But what Feynman goes on to then talk about is this. He says, is the sloshing of water the same as the wind? Now when we look at the sea, we can see lots of various different movements of the water going on. There is the tide, that slow rise and fall every time the moon goes overhead or underneath, raising the entire sea level. Or perhaps there is the oceanic currents swirling around in the different ways, or the waves moving on the top. Is it as simple to say that the wind is just like an ocean of air that we are stood in? Well, the answer is unfortunately no. That there are different things going on in wind than is going on with the water. And so that is a situation where we cannot simply say this is like that. What we have to do there is understand the differences in order to understand those elemental things that are causing the phenomena that we see. I have here my Galileo books. These 3 books here, the ones written by Galileo himself, describing a new way of asking questions about the universe, the scientific method. He lays out in these 3 books a way of finding partial answers to all of those questions that we have. Now, Feynman stresses that we're not going to go deep into the hows and the whys, but he then does talk about how the scientific method is applied. What does it mean to say that we understand something? Well, Feynman likened it to observing a game of chess being played. He said that our world is like a game of chess being played by the gods, and that we are the observers of the game, and that we may study the moves being played. For example, a knight can move like this, and a pawn like that, and a bishop just like that, and that we might know what the knight, the pawn, and the bishop can do. But one of the things that we would have to do is we'd have to really carefully watch, how we could then, for example, then knock out that bishop with a move of the pawn. That all of this is a level of complexity beyond understanding how they can move. It's then an understanding of how they can take each other, understanding of the strategy that is beyond the simple movements of the game. And yet this is what physics is like. In fact, all of science is like this. That we can, by observation, study the very basic rules of the game. And from that we infer a scientific understanding. How do we know if we have understood the rules of the game? Well, Feynman describes that there's 3 main ways of doing this. And the first one is by simplifying the picture. So I've taken off the board all of the pieces except 2 here, in the attempt to observe exactly what this one piece is doing, to understand the rules at play with just this one piece, and simplifying it so that all of the pieces are removed. I'm going to move my bishop along here and along there, and then I think I've checkmated, but I haven't really. By focusing on just the one thing, I can infer some understanding of that one thing's part in this game. The second way is to check to see if rules are being followed. Take, for example, this situation here. We have one bishop here that is on a black square and one bishop that is on a white square. And what I know is that this bishop here will never ever sit on a black square. There's no movement that it can do to result in it ever being on a black square. So we can suggest that this is a rule, that that bishop will never end up on a black square, and then we can test it. We can observe in the game to see if it ever does end up on a black square. Now, Feynman uses a brilliant example at this stage of something unusual happening in this game of chess, and He describes what happens when you get a pawn all the way to the end, and in the process of queening, it gets swapped out for a bishop. And now what we can see is there is now a bishop on the black square when perhaps you weren't expecting one. And so this changing a pawn into a bishop was not a part of the original rules that involved no bishops on black squares, or at least you'll have one on the white and one on the black, and if you've already got one on the black, you wouldn't expect to find another one on the black. But if a pawn has, in queening, turned into a bishop, then all of a sudden you will find a bishop on a black square when you weren't expecting. So what is clear here is that our most simplistic rules have caveats, that there are situations where new rules might apply. And all of physics is like this. We might think that we have understood, and indeed everything we look for is observed to be true, but then we find that there are certain situations where new rules apply. And when those new rules apply, we might find different results to the ones that we originally expected to gain. The third way of finding out if our understanding is correct is through the approximation. To understand approximately how somebody plays is of great advantage. Now, if you ever played me in chess, you'll probably spot that my methods are rather crude. What I'm very likely to do is use my knights, and I'm giving away some trade secrets here, to go after the bishops and the rooks of the opposite players. Having got rid of those, I would then at least make it look like I'm going for those players, whilst always looking for an opportunity to take the queen. I would protect my knights at all times, and only use my other players if absolutely necessary. That is my approach. Understanding approximately what my tactic is the next useful thing in physics. Understanding approximately what is happening, though quite crude, is actually a way, after we have identified the rule in the simplistic case, after we have then tested it to see if it is always true, making an approximation to see if this is approximately what happens in a more complex situation, and assessing that approximation. That is the very next step. So here is Nuclear Physics by Heisenberg. Here's De Broglie's Atomic Radioactive Transmutations, Spectrum Analysis by Roscoe. And then down here we've got all sorts of things, the textbook of physics on sound. All of these different areas of physics are all describing individual sets of phenomena. But then the next stage with working how physics works is to amalgamate. See, what we understand is that if we had a book that was on X-rays, that we might understand that that was a part of the electromagnetic spectrum. And that electromagnetic spectrum was all a part of magnetic and electric fields, which ultimately is all to do with potential energy. So you can see that even though these things can be grouped into like whole subject areas, whole topics, that what we can seek is amalgamations between these subject areas. That is one of the things that physics likes to do. And with any new thing that's found, it's a case of finding a place for it within the structure of our understanding. We could ask whether or not all of the laws of physics are capable of being amalgamated into one single law of physics. A grand unified theory has been the pursuit of modern physics for the last 70 years. Scientists like Stephen Hawking and friends have been very interested in seeing whether or not there is just one central law of physics that includes all of the areas that we understand. One of the problems is the fact that there's always new things to find out. And it quite often means that the only grand unified theory that we're likely to find is going to be of an approximate nature to make room for the things yet unknown. And what we must then do is find that those things yet unknown, when their explanations are known, find that they are consistent with the grand unified theory that we already know to exist. So that is the challenge, to discover that thing that is in the background, that connects all things in a way that is open to new information and new developments in physics as we discover them.